All right. Hi, class. This is Brian. I want to start by talking a little bit about a new probability distribution which we'll be using in this module. We really only looked formally at one of them, which is actually we've looked at the normal distribution and the t-distributions. So the probability distribution which will be important in what we'll call goodness of fit tests is called the chi-square distribution. So just to introduce the idea a little bit, I'm going to just show a couple things in StatCrunch. So I'm going to simulate some data from a normal distribution. I'm going to put 500 rows, one column, with a mean of 0 and a standard deviation of 1. So remember, that's a standard normal distribution. Okay, so that's just creating just a whole, if I just went down the list, now these are all just random numbers that have been generated by the software. If we wanted to kind of check and see if that really is coming from a normal distribution, we could look at a histogram, and that might convince us that it is normal. I'm going to select this column, and I'm going to create the histogram and look at it, and we should hopefully see this bell curve. Oh, this is so beautiful, isn't it? There's a bell curve. There are actually other tests that we can do statistically to verify whether or not some data is coming from a normal distribution. I can do something called a goodness of fit test, a normality test, and this is very, very simply put. It runs a hypothesis test, and it'll give me a p-value. And if that p-value is large enough, I would only conclude that the data is not normal if that p-value is small, just like we did for other hypothesis tests. The null hypothesis is that the data is normally distributed. The alternative is that it's not. And this p-value is very high, we would not reject the null hypothesis. And of course, this data is normally distributed because that's how it was simulated. Okay, now the reason I was spending a little bit of time looking at normal distribution data is I'm going to pull up that histogram again, and I wanted to just look at that side by side with the normal probability calculator, just so we can see what the standard normal distribution looks like. Okay, so this is the standard normal that this thing is, where the data is simulated from. So I'm going to do a little modification to this data. What I'm going to do is I'm going to compute an expression. I'm going to take all of the values, I'm going to square them. So I'm going to take the data in column normal 1 and square it, and that'll be, I'll call this new column chi SQ. I'll call it chi square 1 just to be consistent with the numbering. Okay, so it'll put this in this new column. So this new data, if I was to graph a histogram of this data in this column, let's look at that. Okay, so first of all, you notice something, that the data doesn't get any smaller than 0. And it has this peak and it trails off really bad. So it's got this tail going out to the right. This is a skewed distribution. This is called a chi-square distribution, and I'm going to show you the calculator for the chi-square distribution, so you can see what the theoretical chi-square distribution is. Now I'm going to put in 1 degree of freedom, and this here is what we'd call a chi-square distribution with 1 degree of freedom. So again, this concept of a degree of freedom is the concept of a degree of freedom is coming up again. We'll talk a little bit about what the degrees of freedom mean in this context a little later, but I just want to show you this would be the theoretical distribution for a chi-square with 1 degree of freedom, and this is what my sample data is. So my point is, if you have a standard normal random variable and you square the values, what you get is a chi-square distribution with 1 degree of freedom. So there's this relationship, and that's the basis for it all. And if you were to take a bunch of different chi-square random variables and add them together, the degrees of freedom increases. So I'm going to show you what 2 degrees of freedom looks like. Okay, so here we see this is not quite as steep. With 3 degrees of freedom, now we actually have a curve that comes up and goes down. 4 degrees of freedom. You can see the mean of the distribution is increasing. Let's look at what 8 degrees of freedom looks like. You have this bump. Look at 15 degrees of freedom. Okay, so you can see what's going to happen as you add up chi-square random variables. The degrees of freedom increases. That's one thing that happens. So this is going to be important because we're going to be looking at a statistic, a test statistic, which should follow a chi-square distribution, and we'll be using that in order to answer hypothesis tests. So what we're looking at is, I'm going to go to the homework now. Here is a probability distribution. We have, imagine that you have okay, so I'm going to clear this and just talk a little bit about goodness of fit. Let's select all, Control X, everything's empty. This is, I'm going to call this my let's say probability. Let's suppose that I rolled a 6-sided die a bunch of times. Let's say probability of each roll 1 over 6, 1/6, 1/6, 6th, 1/6, 1/6. Okay, so I have the probability of rolling a 1 through a 6 are all 1/6, and let's say I did this thing like many times. Let's say I got 356 ones. Let's say I got 255 twos. Let's say I got 401 threes, 372 fours, 355 fives, and 321 sixes. Now I want to just use this data to determine, is this a fair die or is this not a fair die, right? The idea is, if I was to roll it a number of times, I should expect to get about 1/6 of my rolls to be a 1, about 1/6 of them should be 2s, and so forth. Of course, that it's not going to be exactly 1/6 because there's randomness involved. If every roll, if every 6th roll was a 1, that would be very suspicious, right? You would expect ones to pop up about 1/6 of the time, but each roll is independent of the previous rolls. Right? The die doesn't remember what number came up, and it's certainly possible that I could get 400 threes and as low as 255 twos, possibly. But I want to know, is that very, very unlikely, or is that within the realm of likeliness? And that's what a goodness of fit test does. And it's very easy to do in StatCrunch. Under the stat menu, you go under goodness of fit and you click on the chi-square test. You give it the observed. I'm choosing the column observed. I named that column observed, so I choose that. And the expected column are in you know what? It doesn't like the probabilities that I typed in. I'm going to just click this all cells in equal proportion. This is to say, if it was a fair die, all of them should be equally likely. It didn't like my 1/6 that I typed in. I think I have to put in, let's put them in decimal. It should be, I know the decimal, it's 0.166667. 0.166667. Okay. Oops. I'm going to go back to that goodness of fit. Oops. So yep, that's what I want. Observed. Observed. The expected is in the probability. And let's compute. So this is what it tells me. Okay. For each of these outcomes, I would have expected from this n, this 2060 says that I rolled the die 2060 times. It just added up all of the numbers in this column. Okay. The degrees of freedom is calculated for me by the number of essentially it's the number of possibilities in this column minus 1. So there were 6, subtract 1, you get 5. And it calculates a chi-square test statistic. This chi-square test statistic, the calculation of it is, it involves taking what you've observed, the difference between what you observed, say 356 for the number 1, and 343, the difference between that and squaring it and doing some other calculation, you end up adding up a bunch of stuff, and then you get your chi-square test statistic. So what you should take away from this is this test statistic from rolling the dice follows a chi-square distribution with 5 degrees of freedom. So I want to just take a look at what a chi-square distribution with 5 degrees of freedom looks like. Okay, this is what the distribution looks like. And so we can calculate what, say, I'm going to change this to greater than. Let's look at what is the cutoff for 5% in the upper tail. So I want to find what's the cutoff, which is going to put only 5% in the tail. That happens at 11. So if I calculated a test statistic that's above 11, that means I have observed some very, very extreme data that's extremely unlikely for a fair die. My test statistic was 37, which if we were to put in 37.1223, hit enter, yeah, this is the probability in the tail. I mean, it's off the chart. You can't even see 37. The probability in the tail is 0.00000057, and this test told me the p-value was less than 0.0001. So, long story short, I would conclude this is not a fair die. It would be extremely unlikely for a fair die to give me some data that's so biased like this, that the number 3 comes up this often and the number 2 comes up so few times. Okay, this is the idea for a goodness of fit test. Now we're going to go and see how we can use goodness of fit test and the chi-square distribution to answer some of these problems. Okay, so this one is fairly straightforward. I'm going to show you how you can use StatCrunch to do all the calculations for you. It's a little trick that I learned. We're given a probability distribution. So imagine this spinner that can come up as a 1, 2, 3, or 4, and the respective probabilities, 0.18, 0.39, 0.24, 0.19. So 18% of the time it would spin and give you a 1. 39% you would spin it and get a 2, and so forth. So n equals 800 means we spin it 800 times. How many times would we expect to get the number 1? Now it's just 18% of the number of times we spun it, which we could just multiply 800 times 0.18 in a calculator. But let's imagine we had a huge number of these things and we didn't want to manually multiply every single one of them. So I'm going to open this in StatCrunch, this probability table, and show you how you can use the goodness of fit test to do this. So let's go to Stat. I'm going to imagine that we spun it 800 times and we only got ones. So I'm going to put, I'll call this observed. This didn't happen, but this is the way I'm going to just trick StatCrunch into giving me the answer. Okay, so I just type in a new column and I put 800 and I put a bunch of zeros. It has to be completely filled in with zeros down below. I want it to have 800 because in the problem it says n equals 800. So now under stat, because goodness of fit, if I choose observed for my observed data, which is fake, but I am just tricking it to calculate this stuff for me, pi, which is the probability of each number I equals 1, 2, 3, 4. So it's not pi, the Greek letter pi. This is just the naming that StatCrunch uses. So don't worry about it. But anyway, you hit compute. You notice that down here in this in the table, it gives me the expected outcomes for each of the four values 1, 2, 3, 4. Just bear in mind that this is all in order. So I could answer the problem using this. So for the first one, it's 144. The next one is 312, 192, and 152. Super easy. I don't have to do the calculation. I just had to trick the StatCrunch into doing a goodness of fit test with some fake data and these proportions. And I was in business. Okay. So let's do a goodness of fit test for this. Here we have 4 outcomes A, B, C, and D, and this is how many times they occurred, how many times we would have expected them to occur, 10, 10, 10, 10. So a goodness of fit test in StatCrunch. Okay, so let's run the goodness of fit test. Stat, goodness of fit test, chi-square, observed in the observed column, expected in the expected column, and let's compute. The output is nice and simple. It gives you the 3 degrees of freedom, the chi-square test statistic, the p-value. It gives you it repeats this table for us. So it gives you the chi-square test statistic, it's 0.4. I really don't want you to, you can use a formula to calculate the chi-square test statistic. It's just a pain, and I don't want you to go through the headache of it. There's 3 degrees of freedom, so critical value. The critical value is based on an alpha level of 0.05. I'll show you again how we get that. We'll pull up a chi-square distribution from the calculators with 3 degrees of freedom, and I want to find where is the cutoff for 5% in the upper tail. It's at 7.814. Let's see, 3 decimal places, 7.815. I have to round it off. And should we reject? We have a test statistic of 0.4, which is not in the rejection region. It's snugly down here. So it's our chi-square test statistics. So this chi-02, it's chi-square. Chi is this X-looking character. It's a Greek letter. Chi, C-H-I. It's not pronounced chi, it's pronounced chi. So we don't reject because chi-square is less than our critical value, and that's it. Cool. Okay, let's skip number 3. Let's look at number 4. So this is a super cool problem. Benford's law is really interesting, and I encourage you to read about it. It's used in forensic forensic accounting, among other things. So you can use Benford's law to determine if people are cooking the books, so to speak. This statistician Benford, actually, I don't know if he was a statistician, but he noticed that some numbers are at the beginnings of some digits are at the beginnings of numbers more often than others. So the numbers 1, 2, and 3 are the first digit more often than 7, 8, and 9 in a lot of situations. And for dollar values, like numbers in ledgers, that's one of the situations where first digits follow the distribution of Benford's law. Anyway, let's look at it's telling us that we have this is the distribution from Benford's law. The number 1 comes up 3% of the 0.301. That's about 30% of the time as the first digit. 2 comes up about 0.176. Let's open this in StatCrunch. It'll be easier to look at. Okay, and in fact, just to understand it a little better, I'm going to create a bar chart with I guess the way to do it is to do a custom calculator. So go to custom calculators. The values are in the digit column, and the frequencies, the weights, are in the probability column. Okay, this will just show you a shape. This is the shape of the distribution for Benford's law. Okay, so this is the values 1, 2, 3, 4, 5, 6, 7, 8, 9. Notice 0 is never the first digit, because if it starts with a 0, you don't write the 0. Anyhow, we want to do a goodness of fit test. So these are the frequencies that have been observed, and these are the probabilities. So under the stat menu, we want to do a goodness of fit test. What was observed is the frequency, and the expected, you can use that probability. Compute and see what we have. So you can see the number 1 was observed 42 times, but it was expected 60 times. The number 2, the digit 2 was observed 32 times, being the first digit, and it was just a little bit off from what was expected. Okay. So let's go back to this problem. The null hypothesis is that there's no fraud going on, so that the first distribution of the first digit should obey the Benford's law. That's the null hypothesis, that this distribution applies. The alternative is that it doesn't obey Benford's law, that there's some other distribution. The test statistic is given to us here. Chi-squares test statistic to 3 decimal places. And the p-value is also given to 3 decimal places. That's 0.037, rounded up to 0.08. Okay, and we're using alpha at 0.05, so that means we would reject because the p-value is less than 0.05. We do reject because the calculated p-value is less than the alpha, the given alpha. Super. Okay, so since we rejected the null hypothesis, and remember the null hypothesis is that the first digits are obey Benford's law. So we've concluded that something funny is going on. So we would conclude that the employee is guilty of some embezzlement, or at least this lends evidence to that. So you would choose A. Okay, let's see one more for this. A traffic safety company publishes reports about motorcycle fatalities and helmet use. The distribution shows the proportion of fatalities by location. The second data shows the location of injury and fatalities for 2,069 riders wearing a helmet. Okay, let's look at this. So, okay, let's see. Let's open the data set in StatCrunch and let's do some work on it. Let's close that. Okay, so what we have is we're trying to determine whether these bikers get injuries with these probabilities or not, or whether this probability distribution applies. So the null hypothesis is that it does. The null hypothesis is that, let's see, the distribution of fatal injuries for riders not wearing a helmet follows the same distribution for other riders, and the alternative is that it does not. So that's what we would choose. The null hypothesis has to prescribe a distribution. The alternative just says, no, something else is going on. Okay, so let's calculate the expected for each of these. This is nicely given to us by the goodness of fit test. So we observed the frequency column, the expected probability, and then just hit compute. And you get it right here. We can use that. Okay, what was expected for the first choice of multiple locations, 1179.33, and then 641.39, 62.07, 124.14, 62.07. Okay. P-value, it's given to you, 3 decimal places, rounding it to 3 decimal places rounds to 0. We would reject the null hypothesis. There is sufficient evidence that the distribution is not what we would expect. So we do reject. There is sufficient evidence that the distribution of fatal injuries does not follow the distribution. So there we go. So from the observed and expected, what we can see looking at those numbers. So for the second category was they seem to be getting more injuries in multiple locations than other, fewer head injuries. No, more head injuries, fewer in the neck, fewer in the abdomen, fewer in all the others. They seem to be getting more head injuries. Motorcycle fatalities from head injuries occur more frequently for riders not wearing a helmet. That's the conclusion. Okay, we're gonna move on to the next section, but first talk a little bit about the F distribution. Okay, the next distribution that'll be important for us is called an F distribution. The F distribution. It allows us to you can, just by looking at this curve, it looks a lot like that chi-square distribution. It's used in what's called the analysis of variance, ANOVA, A-N-O-V-A for short. So like all these distributions that are very common, it is determined by some parameters. It's got 2 parameters, what's called a numerator degree of freedom and a denominator degree of freedom. So as you change the numerator degree of freedom and the denominator degree of freedom, you get a different shape. This thing is going to be different depending on those 2. In fact, the chi-square distribution is a special case of an F distribution. But I don't want to get into that right now. What I will say is it's one of these distributions where it describes a random variable that only takes positive values, from 0 upwards. So when we're looking at extreme values, we're going to be looking at values that are in the tail. So I'm going to change that to greater than and say 0.05. So like this is to say if I wanted to look at what's the top 5%, that would be the rejection region if we were looking at a test statistic that follows this, right? We're looking at this upper tail for rejecting. So how exactly does this work? First, I want to just mention the calculation of a test statistic. Like I said, it has these two degrees of freedom, the numerator degree of freedom and the denominator degree of freedom, because the F distribution, the statistics that follow it are fractions. You've got a numerator and a denominator, and you'll see exactly how that is here. I'm going to look at this so-called ANOVA table and just show you how we calculate the values in the ANOVA table. So here I'm going to pause and pull up my calculator. So let's. All right, so the calculation for an ANOVA table is actually not that bad. Basically, we just go down in this. First of all, the simplest thing is this. Okay, well, let's just talk about what is an ANOVA table. So ANOVA, analysis of variance. So when we did linear regression before, you may recall seeing ANOVA tables as part of your output. We didn't really spend a lot of time on them, except for, I think we used the F statistic to make some conclusions. Here, let's get a little bit more into it. In what this sum of squares is a square deviations. So you have some observed values and expected values. You take the difference between what you observed and what you would expect, take all those deviations and square them all. That would be the sum of the squares of the deviations. That's what's going to be in the error. So the sum of the squares for each of these two categories is that's essentially the how we measure variation. You take the deviation from what you would expect somehow, and then you square it, and that's going to be variation. That calculation, that's what's used in the calculation of variance, you may recall. So anyhow, we first want to look at the total row, the total sum of squares between treatment and error. It's simply going to be the total of those two numbers. So I'm just going to add 358 plus 4206. Okay, so 4564. And the degrees of freedom, add those up, 4 and 28. I actually do that in my head. 32. Okay, now we have the next column, which is the mean squares. So it's, you know, that the mean is a word we use for the average. So what we're looking at is how much variation is there per degree of freedom. It's, you take the sum of the squares and you divide it by the degrees of freedom, and that gives you the mean square. Okay, so 358 divided by 4 gives you the mean square for the treatment, 89.5, and 4206 divided by 28, that's the mean square for error, 150. Let's see, 3 decimal places, 214. Okay, now an F statistic, like I said before, it's going to be a fraction. You have a numerator and a denominator. Well, the numerator is going to be the mean square for the treatment, and the denominator is the mean square error. So I'm going to take 89.5 and divide that by 150.214. That fraction is my F statistic, 0.596. I have to round it up, 0.596. That's how you fill in an ANOVA table. So all of this stuff just comes from those numbers here. Okay. Now, the way we can use ANOVA tables is actually let's take a quick look at this F statistic. Okay, let's say we had this ANOVA table. I'm going to ask, is this a very unusual F statistic for this situation or not? Well, let's look at the distribution. The numerator degrees of freedom is 4 numerator degrees of freedom, and the denominator is 28 degrees of freedom. Let's put this this test statistic that I found, 0.596, and just see. It says, so this calculator is telling me that 0.668, that's the probability to the right of that value, 0.596. So this is telling me that, well, about 67% of the time, one would expect a test statistic more extreme than this. So this is actually a very, I would say, it's probably quite common, right? It's like 2/3 of the time, your test statistic is going to be even bigger than that. So this is not a very extreme F statistic to get in this analysis of variance. So our p-value would be that 0.668. And how we interpret that and how we make conclusions of that, we'll look at in the next problem. Okay. So the data in this accompanying table represents the number of corn plants in randomly sampled rows, 17-foot by 5-inch strip. That doesn't really matter. For various types of plots, an agricultural researcher wants to know whether the mean number of plants for each plot type are equal. So let's just look at the data briefly. So we have 3 types of plots: sludge plot, spring disc, and no-till. So this is the number of plants in each of the 6 plots. So there are 6 from each of these. Okay, so the null hypothesis in this case is that all these 3 populations actually have the same mean. The alternative is that one of the populations has a different mean. So the null hypothesis is that mean for the sludge plot, the spring plot, and the no-till is the same. The alternative is that at least one of them is different. They don't all have to be different. At least one of them is different. Okay. So in order for us to use a one-way ANOVA procedure, we have some requirements, some theoretical requirements that need to be satisfied. For one thing, we need to have, so we have 3 different populations. We need to have a simple random sample from each of the 3 populations. There must be k simple random samples. In this case, k is 3. 3 simple random samples, 1 from each of the 3 populations. The populations should have the same variance. If they have very different variances, then the theory doesn't, the conclusions don't really hold. And we also assume the populations to be normally distributed, and the samples have to be independent of each other. So those are the requirements we have for a one-way ANOVA. So let's see. It gives us the ANOVA table, but let me show you how we would actually generate that ourselves. Let's pull up our data and go to take it to StatCrunch. All right, I'm going to run under Stat, you have ANOVA, one-way ANOVA. I'm going to select all three of these columns, hold down Control, and then click them one by one. And I'm just going to hit Compute to get my standard output from a one-way ANOVA. So it gives me, so you can, let's scroll down and take a look. So you can see I get the same, let's put it side by side. You can see I get in my ANOVA table, I have for my factor, the columns, 2 degrees of freedom. Excuse me. I have 2 degrees of freedom for the factors, for the columns. Each column represents a different factor, so-called factor. We have the sum of squares, this is rounded off, the mean squares, the F statistic, and the p-value. So the p-value is small. That's what we look for. We look at that. The p-value is small. We want to reject the null hypothesis. There is sufficient evidence to support the alternative. That's the bottom line. You reject based on the p-value. And the reason was it was smaller than our alpha, right? The alpha was 0.05, the p-value was smaller, but you reject. Side-by-side box plots. You know what? Let's just see how we would actually create the box plots ourselves, even though it's given to us just for practice. Under graph, if you choose box plot, again, select each of those, and I'm going to just look down the list. I want to draw the box plots horizontally so it looks the same, and I'll use a marker for median. So let's compute and let's just look at it. You can see that. So this is how we could create side-by-side box plots from StatCrunch. It looks the same. So let's continue and just say something. Okay. Just from looking at it, it really looks like this spring disk population is very different from the other two, doesn't it? And that's the conclusion we would make from visually looking at it. We would, so the question is asking us, do the box plots support the results? I would say yes. They do support it because it looks like one of the, at least one of them, the mean is significantly different from the others. It certainly looks like it. Although it's worth mentioning that the box plots don't show you the mean, they show you the median. If we wanted to actually look at the mean, let's edit this and show the mean in green. Haha. The mean isn't that far off from the median, but still, it's not the same as the median. But yeah, one of those means is very different from the others. So, yeah. All right, so this next part is quite tricky to do if you don't know how to do it. So we're looking at it says use technology to make a normal probability plot of the residuals. So, okay, what is the normal probability plot of the residuals? How do you create that? So what you can do, let's go back to our analysis of variance calculation, and I'm going to change the inputs. I'm still going to use those three, but if you go down to the bottom, you can scroll down, and I'm going to save residuals. Okay, because I want to plot all the residuals in one plot. And so when I did that, okay, that's fine. All of my residuals are right here. See, all of those residuals. What I'm going to do is I'm going to create a new column, called like all residuals. And I'm going to just copy everything. So select Control-C, Control-V. If you're using a Mac, you'd use Command-C, just like you normally would, copy and paste. I'm going to put everything in this one column. I don't know another way to do it without putting it all in one column. So, okay. So I put all my residuals in one column. I'm going to do a graph called a QQ plot. A QQ plot is a quantile-quantile plot. It's what gets us to match up quantiles. So what we're going to get is some plot that looks like we have over here. I'm going to select everything from the all residuals column, and I'm going to put the normal quantiles on the y-axis. If you notice, in each of these three plots, z-score is on the y-axis and residuals are on the x-axis. That's how I want it. So I check off normal quantiles on the y-axis, and that's it. So I'm going to just click compute, and we'll see what this looks like. Now you can see what you have is this scatter plot where they kind of squiggle along. What this is doing is it's putting the it's for each of these. I could describe it very briefly. The each of my residuals, okay, is taken. The lowest residuals are the residuals in this column. Say we're sorting them in order, okay, from smallest to largest, and we're plotting those against quantiles for the normal distribution. You know what? It's more than we're going into in this course. I'll put that into another video maybe. But let's just compare these graphs and see which one matches, okay? So let's look at this shape. These bars are prediction intervals or kind of tolerance intervals, I think, but the main thing is comparing this line and comparing this shape. Really just the dots. These look very much, the pattern of the dots looks pretty much right on. You can see that pattern is there. I think we can say for sure that this is not it, right? This is scattered and crazy. And this one, let's see. It looks like, I would say, this is very hard to, it's hard to choose. It's very hard to choose. They both, I don't think this one's quite as close. I really think that this one is better. Let's just look one more time. Yeah, I would say without a doubt, this one is what I want. Okay. Okay. How does it compare? Really what we're looking for is we want to see this look fairly linear. And it looks pretty good. It's approximately linear. If it wasn't linear, it would be a lot different. So that's fine. Okay. So we'll just take a look at 8, and this will give you a good sense of how you do these ANOVA tests. So again, we're given stock analyst wonders whether the mean rate of return of financial, energy, and utility stocks differed over the past 5 years. Simple random sample of 8 companies from each of the 3 sectors. So let's take a look at the data. Okay, so we have three columns. Let's again bring it into StatCrunch because that's where we're going to do this ANOVA test. Meanwhile, remember, the null hypothesis in all these cases is that all 3 means are the exact same. The alternative is that one of the means is different, at least one. Okay, we're going to look at normal probability plots it tells us that the normal probability plots indicate that the 3 samples come from normal populations. What are normal probability plots? They're QQ plots. So actually, we can graph individual QQ plots for them if we wanted to. We can select all 3 and just compute QQ plots. And this is it's graphing the normal quantiles, pairing them up with the values from smallest to largest, saying if they were from a normal distribution, and there were 8 observations, we're taking the 12.5th percentile, the 25th, 37.5, 50th, and so forth. Like, what would those values be? And kind of pairing those up. What would those z-scores be? So all of these follow the line pretty well. That's what it's saying when it says the normal probability plot indicate that the sample data comes from normal populations. Okay, so as long as the samples were all independent and random, he says he did simple random samples of 8 companies from each of them. So yeah, I think that's fine. As long as we have independent simple random samples, yeah, we have. Well, actually, we have to check the variances before we can conclude that all of the conditions are met. So let's actually check that. Let's do a summary stats for this, for these 3 columns, and just compute. We want to compare these variances. The variances of this sample data, 26, 24, 20, those are pretty close to each other. I would say those are not different enough for us to conclude that the variances are different. So they have about the same variance. So let's see, independent of each other, populations are normally distributed and have the same variance. Have the same variance. Sorry, I was just reading in detail. They have about the same variance. Okay, so let's do the ANOVA test for this data. Let's stat ANOVA one way. Select our columns, compute. Standard output is fine. In fact, let's actually go back to the options. I want to show you something else you can do. Edit. Notice this test homogeneity of variance. Just check that off, and it'll test whether the populations have the same variance. Here's something down here. Levine's test for homogeneity of variance. This is a hypothesis test for variance. So what it's looking at is, it's asking the question, do the populations have the same variance or do they have a different variance? So what the p-value is very, very high, 0.93, which would lead us to the conclusion that we do not reject the null hypothesis. So we do not reject the null hypothesis that the populations have the same variance. So that's a hypothesis test to decide whether or not populations have different variances. But we just eyeballed it, and that was the same conclusion. We eyeballed it. But we should really use that as our deciding thing. That's a hypothesis test. That's much more quantitative reasoning. So anyway, get our F statistic. It's given right here, 2.05. And the p-value is actually fairly big. The p-value is 0.15, 3 decimal places, 0.154. There is not enough evidence to reject the null hypothesis. Right? If we're doing this at a alpha at 0.05, we need a small p-value, smaller than 0.05. It's not So we cannot reject the mean. The mean rates are different. So we would stick with that null hypothesis that the means are all the same. Box plot side by side. We can do that, right? Graph box plots. Select your columns. I think it puts a line. I don't have to mark the median myself with red. Oh, but we don't want them horizontal. Ugh, horizontal. Who wants that? Edit the options. Change it to draw boxes. Oh, we don't want it vertical, I meant to say. We want them horizontal. We want them horizontal. This is what we want. Let's just compare. Utilities, energy, financial. Let's see. Let's compare. Is it this one? Looks pretty good. I'll go with that unless this other one is better. Energy. Oh, it's wrong. It should be utilities, energy, then financial. That's wrong. First is utilities and energy, then financial. Ha, they're trying to trick me. Okay, cool. So, okay, you can use those ideas to do the homework problems, and the same kinds of tools will be useful on the other problems that I skipped. All right, wish you the best, and I'll touch base with you a little later in the week with some more info. All right, bye.